format, and this is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to be discussing the solution of electrostatic boundary value problems using spherical coordinates. Previously, we looked at the solution of boundary value problems in rectangular coordinates and also cylindrical coordinates. In both cases, we made use of a technique called separation of variables. I'm going to do the same thing here. With spherical coordinates, we're going to be talking about some functions with which some of you might not yet be familiar. So I'm going to spend a little bit of time talking about those features, and then I'll talk about the actual solution of problems in a forthcoming video. Right now, let's begin with Laplace's equation. Laplace's in spherical coordinates. Laplace's equation in spherical coordinates is whatever r squared partial derivative with respect to r of r squared partial derivative of the potential with respect to r plus whatever r squared sine theta plus partial derivative with respect to theta of sine theta partial derivative of the potential with respect to theta plus 1 over r squared sine squared theta second partial derivative of the potential with respect to phi. We're going to use separation of variables. What that means is that we're going to replace this potential v, we're going to assume that it has the form of the product of three functions. So in other words, this is a function of something that's only a function of r times something that's only a function of theta times something that's only a function of phi. Okay, I'm not going to read this off, but basically this is the same equation as this, with the v's replaced by r, theta, and phi. Now, since in this first term, theta and phi don't depend on r, I can pull those two factors out. In the second term, since r and phi don't depend on theta, I can pull those terms out. And since r and theta don't depend on phi, I can pull those two factors out. First term is function theta times function phi over little r squared, derivative with respect to r of r squared, and the derivative of the function r with respect to r. working towards isolating dependence on a variable in each term. So in other words, ideally I'd like to have something that only depends on r, plus something that only depends on theta, plus something that only depends on phi. And then that way I know that the only way that equation can vanish is if the terms are equal to constants in some fashion. What I'm going to do next is multiply through by little r squared, and then divide through by the potential v. So in other words, I'm going to divide every term through by the function r times the function theta times the function phi. And that will give me now see, if I look at my first term, only a part r appears in there, and it appears nowhere else. So far so good. Theta only appears in the second term, but unfortunately it also appears in the third term. So whereas we've got one term with just theta here, but theta appears over here, so we've got a term that has mixed variables. So we've got dependence in this last term on phi, and also on theta as well. So what I'm going to do is I'm going to tackle this radial term first and solve that, because I know this has to be equal to some constant. Now before we chose constant either k squared and or an m squared minus m squared, as the case might have been. As it turns out, this time it's more useful to call this product of two integers. So in other words, we'll assume that this has a value, this function has a value of L times L plus 1, well, where L is an integer. And the reason why we're making the choice like this will become apparent once we work through the rest of the analysis here. So anyway, we're going to assume that this differential in here has this form. We're going to do the math over here. And that is r squared times the second derivative of the function r with respect to r, plus 2r times the second derivative, the first derivative of the function r with respect to r, minus L times L plus 1 times the function of r. Solutions to this expression are either r to the L or r to the minus L plus 1. Your answer then is going to be some linear combination of these two functions. Okay, so now we've got the radial term figured out, so I'm making progress here. I'm going to substitute in L times L plus 1 up here, and I'll just have a differential equation that's only in terms of the angles. how do I proceed from here? After all, this only has dependence on theta, and this has theta and v. What you want to notice, though, is if I look at this function here, we get the second derivative of the function v with respect to phi over v. Last time around, when we were doing cylindrical coordinates, we encountered a term like this. There was no sine squared down there below, but if we multiplied through every term by sine squared theta, we could isolate this, and we know that that has to be equal to a constant. Now our function again has to be single value. So just a reminder of what theta and v represent. We're assuming that our z-axis is a little special here. We're treating it a little bit differently from the other axes, because I'm going to define my angle theta with respect to z. So in other words, theta just measures the angle down from the z-axis down to r, okay? And theta only has values from 0 to pi. It is your polar angle. And phi represents the azimuthal angles. And unfortunately, I'm running out of room here. So azimuthal angle goes from 0 to 2 pi. Just in the same way with cylindrical coordinates, you have to wind up back where you started. You have a single valued function. That also has to be the case when you're dealing with spherical coordinates. So as we go all the way around the z-axis, we wind up back where we started. Your function has to have the same value. The only way that can happen is if one of your function phi times the second derivative of the function phi with respect to phi is equal to minus m squared. In that case, the solution to phi is going to be some linear combination of sine and phi and cosine and phi, which are single valued functions. Since I'm running out of space here, I'm going to replace that with minus m squared over sine squared theta. Now I've got one equation and one unknown, second order differential equation. Solutions to this are called associated Legendre polynomials. And the way you represent that is with the capital letter P, with the subscript L and the superscript N, and as a function of cosine theta. And why is that? Because your answer is always going to be a function of cosine theta, not just sine theta. Generally speaking, then, your potential phi is going to be some linear combination of all these functions tacked together. So it's going to look like something of RL, linear combination of R to the L, R to the minus L plus 1, times some linear combination of sine and phi, cosine and phi, times your associated Legendre polynomials. And by the way, if you're wondering here, this is the second order equation, right? So that means you've got two solutions, and yet I've only written down one solution. Well, the answer is there is a second solution here, but we do not deal with that. It's not applicable to the present problems, shall we say. Okay, so these are the kinds of problems that we encounter in graduate level of electromagnetism. Undergraduate electromagnetism, we assume that we've got azimuthal symmetry. And we have azimuthal symmetry. That means there's no phi dependence. And when there's no phi dependence, that implies that m is equal to 0. Dependence on phi is going to drop out. And we'll be left with this second order differential equation. And solutions to this equation are simply Legendre polynomials. And we write those as P only with subscript L as a function of cosine theta. And therefore, your solutions are going to be some linear combination of R to the L times R to the minus L plus 1 times a Legendre polynomial. Again, that's only when you have azimuthal symmetry, which are the only kinds of problems we deal with in undergraduate electromagnetism. Azimuthal symmetry means that if I go any way around the z-axis, so whether here, here, or here, there can't be any dependence on phi. So in other words, your function isn't going to change as you go around the z-axis. Now, it'll change this way, but not this way. Okay? Talk a little bit more about Legendre polynomials and what form they actually have. I've just written down a couple of symbols here. It'd be nice to know what it represents. So the nice way of doing that is looking at something called a generating function. And to do that, I'm going to start with the expression for the potential due to a point charge. I'm going to call this horizontal axis the z-axis. It doesn't really matter which way I orient it, but just rather draw it this way. Okay? I'm going to assume that I have a point charge that lies on the z-axis. And I'm going to evaluate the potential at some point up there. So distance r away from the origin. And I'll call this distance that q is from the origin r prime. I'm going to write this out in terms of the square root of the sum of the squares. And that's equal to 1 over r dot r minus r dot r prime plus r prime dot r prime. Since r is, we've got the dot product of two r's, that's just r squared. And we've got the dot product of r prime and r prime, so that's just r prime squared. And in the second term, it's just going to be 2 times r prime times cosine of angle. Because we take the dot product, that's equivalent to taking the magnitude of each of the vectors times the cosine of the angle between them. And there's no phi dependence propping in here because we're assuming that we're only dealing with problems of azimuthal symmetry, which is why you only have theta and no phi. Now, if I assume that my observation point is further away than my source, in other words, if I assume r is greater than r prime, I can expand this, make an expansion. So what I'm going to do is I'm going to pull r out of the denominator, or out of the radical. And I'll give you q over 4 pi epsilon naught r. And that'll be 1 over the square root of 1 minus 2r prime over r cosine theta plus r prime over r quantity squared. At this stage, it's convenient to make a change of variables, basically, because I don't want to keep writing them into cosine thetas and r primes over r. So I'm going to write cosine theta as x, and I'm going to write t equal to r prime over r. And therefore, this, whatever this radical sign becomes, whatever the square root of 1 minus 2tx plus t squared. Now, please bear in mind, x and t do not represent position and time, okay? Just making a change of variables, because I don't want to write out a bunch of terms with this, so just rather use one variable for that. I'm going to go ahead and make one further change of variables, and I'm going to assume that y is equal to 2tx minus t squared. I've written my expression of changes of variables and all that, and it's basically whatever the square root of 1 minus y. If y is less than 1, I can make a binomial expansion, or power series expansion. That is equal to 1 plus minus 1/2 times minus y. plus minus 1/2 minus 3/2 minus y squared over 2 factorial. Plus minus 1/2 minus 3/2 minus 5/2 minus y cubed over 3 factorial, and so forth. I'll wind up 1 plus 2y plus 3/8 y squared plus 5/16 y cubed, and so on and so forth. Now I'm going to plug this, what y is in terms of tx, t and x, back in here. So whatever my radical becomes, one plus 2tx minus t squared that should be a half there, not 2. Reading this off. Once again, this is 1 plus 1/2 times 2tx minus t squared plus 3/8 times 2tx minus t squared quantity squared plus 5/16 2tx minus t squared all cubed, and so forth. So look at this section of the board muddled. I'm going to go ahead and work out what each of these terms is. So the idea here is I'm going to multiply everything out and gather terms that are have a common factor of t, t squared, and so forth. Two tx minus t squared quantity squared is equal to 4t squared x squared minus 4t cubed x plus t to the 4th. Now calculating the cubic term. So multiplying out everything, we wind up with 8t cubed x cubed minus 4t to the 4th x squared minus x t to the 4th x squared. We ran out with 2 terms here, I think. Let's see, do that again. Nope, that's right. Minus 8t to the 4th x squared plus 4t to the 5th x plus t to the 5th times x minus t to the 6th. Okay, so collecting terms, we've got 1 plus tx plus t squared times 3x squared minus 1 all over 2. So basically we're combining this term with this term. Now for the t cubed terms. We wind up with t cubed times 5x cubed minus 3x over 2. The coefficients of the t's are in fact just Legendre polynomials. We can write this as a summation L equals 0 to infinity t to the L times PL cosine theta. So by expanding out terms, I can actually generate Legendre polynomials. And of course, as you can see, this gets very messy very fast, and as you get involved with higher and higher order terms, there's a greater chance of losing track of something. So, but these are the first 4 terms of the Legendre series. And let's say, for instance, that you wanted to know what if r prime were greater than r? Well, you just switch those coordinates around, and you'll still wind up with an expansion of this form. I'm going to kind of bring everything together, basically what your solution is going to look like, and then also some characteristics of Legendre polynomials. Your solution, V, is going to be of the form summation L equals 0 to infinity of some coefficient AL times RL plus some coefficient BL times R to the minus L plus 1 times the Legendre polynomial PL cosine theta. And it's interesting to do that expansion of potential due to a point charge and see that in fact you just get this series back, which is what we derived using the separation of variables technique. And oftentimes when you're talking about some of the relations with Legendre polynomials, instead of writing it out as cosine theta, we replace that with the variable x just for brevity. Okay, so your first term, or your 0th order term, is equal to 1. First order is just equal to x. Second order is equal to 3x squared minus 1 over 2. And third order is equal to 5x cubed minus x. interesting to write down some properties. Anyway, I said that data goes from 0 to pi. And when you do the integrals over x instead of theta, you'll see that it goes from -1 to 1. But anyway, let me get back to these polynomials. If I evaluate the 0th order Legendre polynomial at x equal to 1, that's obviously always going to be 1. First order is also going to be equal to 1. Second order, you're going to wind up with 3 minus 1 all over 2. And therefore that's equal to 1. And third term is also equal to 1. So it doesn't matter what order of the Legendre polynomial you're looking at. It's always going to have the value of 1 when you evaluate it at 1. That's the first thing you want to know. Now how about -1? Zeroth order is obviously still going to be 1. First order, -1. Second order is going to be 1 again, and third order is going to be negative. Therefore, by induction, Legendre polynomial evaluated at -1 is going to be -1 to the L. So if your Legendre polynomial is even, it's going to have the value of 1. If it's odd, it's going to have the value of -1. How about 0? Well, if I look at the odd terms, odd polynomials, odd order, I see that those are always going to vanish. And by the way, we did this by induction. There's a way of proving it more rigorously. And when you take math physics, you'll probably be assigned a problem for doing just that. But for now, we're just going to observe the features of it rather than going through a bunch of proofs. So anyway, at 1, it's 1. At -1, it's going to be -1 to the L. If you have an odd order, then your Legendre polynomial will vanish. Even, however, let's see. P naught is 0 is equal to 1, and P2 is 0 is equal to -1/2. Right away, it's not obvious what kind of pattern this is going to follow. In fact, it's going to be a little bit more complicated than these expressions. Just write that down for an odd Legendre polynomial at 0, that's equal to 0. Even, however, is a little bit more complicated form. That's going to be equal to -1 to the L all over 2 to the power L, L factorial, and 2L minus 1 double factorial. In case you're unfamiliar with the double factorial, basically what that means is that you're taking the product of, well, it works like a regular factorial, only in this case you're only looking at odd factorials. So in other words, this is going to go from 2L minus 1, 2L minus 3, down to 7, 5, and 3. And likewise, if you have a 2L double factorial, a product of all the even numbers. So it's going to be 8, 6, 4, 2, and so forth. And you don't need to memorize this, but it's a good idea when you're working any of these kinds of problems to have a cheat sheet where you've got these basic relations noted. It just makes life a whole lot easier. So let me just double check this. Make sure I didn't leave anything off. No, I didn't. Okay. Another useful formula is Rodriguez formula. And what that does, it enables you to generate Legendre polynomials. Generates Legendre polynomials. It's 1 over 2 to the power L over 1 over L factorial L derivative with respect to x of x squared minus 1 to the L power. And when you're working these problems, you also want to know about the orthogonality of these functions. If I integrate the Legendre polynomial times another Legendre polynomial over the interval, in other words from 0 to pi, that is going to be equal to 2 over 2L plus 1 times the product of delta L times L tilde. So in other words, you only have non-vanishing solution here when the L and L tilde are the same value. And if you're more comfortable with writing this in terms of cosine data, that's the interval from 0 to pi, PL of cosine theta times PL tilde of cosine theta sine theta d theta is equal to 2 over 2L plus 1 product or delta L tilde. So just written this in different variables. Here it's written more concisely in terms of the variable x, and here we've written more concisely in terms of the variable cosine theta. And of course, when you make a change in variables, that's why you have a sine theta out front. That'll get gotten rid of when you go from here over this description. And furthermore, you'll notice the limits of integration. So we're going from 0 to pi. But basically, that's the same thing when you change over the x variable of going minus 1 to 1. So either one of these, again, whichever one you're comfortable with, you will be using this a lot when you do electrostatic boundary value. So we're making use of the orthogonality. The last thing I want to show you is a set of relations between various Legendre polynomials, basically between different orders of Legendre polynomials. first one just gives you relation between one earlier polynomial and the second order less, and PL, and the other ones give you a Legendre polynomial in terms of derivatives. And the last one I find especially useful. And that's 2L plus 1 times p sub L is equal to the first derivative of p sub L plus 1 minus first derivative of p sub L minus 1. This form is really useful because if you're doing an integral, if you've got something that's got a PL in it, and you know how in the world you integrate that for unknown L or for arbitrary L, well, you can write that in terms of its derivatives, and then you take the integral of the derivative, and the answer will fall right out. So this recursion relation is especially useful in my opinion. Okay, so you don't have to memorize all of this. Don't recommend that you do, especially if you've got this many terms. But I do recommend that you have a cheat sheet on hand whenever you're working through these problems, so you don't have to hunt through a textbook to find something that you're not even sure what you need. So these are it's a pretty good list there for handling anything that you might encounter in underground electromagnetism. We've really barely scratched the surface of Legendre polynomials, and I do recommend highly that you consult Mary Bose's book on mathematical physics. She's got a lot of great problems on using Legendre polynomials, and as true mathematicians do, she's got all the proofs of why these relations hold, and she gives you problems where you show that these relations hold, generally speaking. So definitely consult her book. George Arkin's also another good choice for discussion of Legendre polynomials. Anyway, that covers everything for the framework that we'll be using. And next time around, we will be talking about how to solve electrostatic boundary value problems in spherical coordinates, and we will be writing our solutions in this form. Next time around, we'll probably get about 4 examples that we'll be doing. Okay, and that concludes this lecture.